Let's see what this looks like in one dimension. Here, we want to minimize the cost function, and let's look at the variable that changes as the bias parameter for a single neuron model. Again, in reality, we'll be changing both the weights and the bias, but for illustration purposes, I'm going to forget the weights and just look at the effect of changing the bias toward what we want the bias value to be. In one dimension, we only have two options for the direction that we can change the parameter in order to change our cost function. We can either take steps in the direction of increasing bias value, or we can take steps in the direction of decreasing the bias value. To minimize our cost function, we need to go in the direction of the negative gradient. In one dimension, this is the negative derivative. So if the gradient is negative, we're going to take a step in the positive direction of the parameter, so increase the bias value. And if the gradient is positive, we need to take a step in the negative direction, so we need to decrease our bias value. Let's say currently the bias value for our parameter is -2. If we make a positive change in the bias value, that is, if we go from -2 to -1, the cost is going to go down. This means a positive change in our bias parameter has caused a negative change in the cost. So our gradient is negative because a positive change in bias caused a negative change in cost. So we have a negative gradient. And with a negative gradient, we want to go in the direction of negative gradient, so we take a positive step in the direction of bias. Now, in our new position, the bias is equal to -1. Again, we see if we take a step in the direction of positive bias, the cost still goes down. So this means that the gradient is still negative at this point, and we should continue going in the direction of positive bias. At this new point where we're at, for a positive change in bias, the cost still decreases. The gradient is still negative, and again, we still should be going in the positive direction of bias. We keep going until we hit this point, and here it's an inflection point where the gradient is flat. We have hit a local minimum of the cost function. If we zoom in very far into this function, the slope is going to be flat at this point. And so with zero gradient, this means it's a local minimum of the function. It's not guaranteed to be a global minimum, but it's a local minimum, and our learning will stop. If we were to keep going in the direction of positive bias, despite having been at the local minimum, the cost is now going to increase. So a positive change in bias now will cause an increase in our cost. This means change in cost divided by change in bias is positive. Our gradient is now positive, but we need to go in the direction of negative gradient. So now, with a positive gradient, we need to go in the direction of negative bias. So this sends us back towards our local minimum. So this is why following the negative gradient, or here it's a negative derivative because we have one dimension, but the negative gradient brings us to the local minimum of our function. The gradient doesn't only tell us which direction to go, it actually also tells us how big of a step we should take. So when the cost function decrease per unit step is big, that means there's a big change in the cost per step. This means that the cost function is very steep at this point, and we should take a bigger step when updating our parameter value. But when the cost function is only changing a little per unit step, this means that the cost function is getting shallow, and we don't want to take oversteps and overshoot our local minimum. So the gradient is small in magnitude, and we would take smaller steps when updating our parameter values. Let's see what gradient descent looks like in 2 dimensions. Imagine we want to look at how cost changes as we change 2 of our weight values. Let's say it's weight 1 and weight 2. In 2 dimensions, we have this cost function that looks like a 3-dimensional values and peaks. These values and peaks are the value of the cost function, and the cost function changes as a function of the values of weight 1 and weight 2. And so let's visualize these three-dimensional peaks and valleys in 2 dimensions with concentric rings, where the valleys will be the center of these concentric rings. So we're smushing down these peaks and valleys into a 2-dimensional representation that looks like a bunch of concentric circles. Let's say our model currently has the values of weight 1 and weight 2 shown here on the graph. The gradient, remember, tells us the direction we need to go. And so the gradient is going to be given by how much weight 2 affects the cost compared to how much weight 1 would affect the cost. If a change in weight 1 would result in a much greater change to the cost function than a change in weight 2, we're going to take a bigger step in the direction of W1 and a smaller step in the direction of W2, and we'll end up taking a total direction that is shown in this dotted arrow. In contrast, if a change in weight 2 would change the cost function much more than a change in weight 1, then we would go more towards alignment with the W2 axis, and we'd go in this other direction shown by this dotted arrow. When we are at different points in our parameter space, the respective amounts each weight would change the cost function differs. So the direction that we should be stepping in will differ depending on where we are in our parameter space. And while the gradient is always discussed in terms of its being this direction in multidimensional parameter space, if it's easier for you, just think of the gradient as the individual changes we need to make to each parameter in order to reduce the cost function. In this visualization, I've shown very big steps just so we can see, but in reality, we're going to be taking lots of very small steps in a highly complicated, very high-dimensional landscape. In summary, the way our neural networks learn is to minimize the cost function, which is some measure of the difference between what our model is currently outputting and what we want the model to output in order to correctly predict our training data. Gradient descent is a way of telling us how we should update our parameter values such that we're going towards the minimum of the cost function. And it's in this way that we're finding the weights and biases in our neural network that will result in predictions that most optimally predict our data.